After Alberto, quite unlucky, but let's try. So I'm the second Mateo, and I'm part of the EP2 group as well. My supervisors are Mario Merino and Eduardo Aedo, and my thesis is stability analysis of magnetized plasma flows for space propulsion, which is quite a nice title, but very general. In the end, like what I'm focusing on about is oscillations in magnetic nozzles. What do they matter? But before that, like what are magnetic nozzles, which by now probably you know because of previous presentations. So let's start from the very beginning. Electrodeless plasma thrusters. They are a novel technology that doesn't need of electric propulsion, electric thrusters that do not employ electrodes, so you don't have a nanode cathode configuration. And so you have longer lifetimes because you are free of erosion, ideally, okay? But still, because you're missing an applied electric field, what you need is like an acceleration device exterior to the thruster. And these are the magnetic nozzles, okay? Which are like, in the end, they work like a nozzle, so they make the plasma expand, okay? And so then you get, kinetic energy from thermal energy. But you don't have like a physical envelope. The thing that is making you expand your plasma is just, the divergence of the magnetic field. And these are E cross B plasma devices in the sense that you have like crossed, vectors of electric field and magnetic field. Experimentally, as Davide was saying, we've seen a variety of oscillations in these devices, okay? And we've also seen anomalous transport, which is like transport, cross-field electron transport, which is not modeled by, classical models. So this has an impact on performance, which is quite important because I've repeated it twice in this slide. So this is also why we're studying oscillations, because we want to, we want to understand what are the conditions for this unstable growth, okay? And then we want to say, how do they drive anomalous transport, okay? We want to characterize this, we want to assess its impact on performance, and then we also want to, maybe in the end, get like a self-consistent modeling for this out of all this study. And like without the need to resort to phenomenological models, as Alberto was saying. Okay, and so these are my goals, what I've already shown you, the goals of my thesis. Now, the instabilities I'm caring about and focusing about are drift-driven instabilities. So now a lecture on instabilities. So and these kind of instabilities are driven by the relative drift between the species composing your plasma, which in my case usually is like a two-fluid plasma, electrons and ions. And you have three main categories for these instabilities. You have stream instabilities, which are like solely driven by interspecies drift. And so like some notable examples are the two-stream instability, quite old, a lot of heritage. Then you have the modified two-stream instability, which is the same, but with propagation of the wave parallel to the magnetic field. And then you have electron-cyclotron drift instability, which Enrique has explained thoroughly in his presentation. Then you have drift gradient instabilities, which you don't only have interspecies drift, you also have plasma inhomogeneities that are driving your instability. And so like some notable names are like the Simon-Ho instability, both the collisional one from the 60s and also like the new modern, collisionless modified Simon-Ho instability, which is the one that is called Simon-Ho in all the papers, like modern literature, to make stuff more confusing. And then you have a very vague definition of lower hybrid drift instability, which is like, depending on the paper you read, is whatever. No? It changes over time, overnight. Okay, and then you have drift resistive, and the shame about this is that I couldn't find a cool GIF to show you in the presentation, but in the end what they are is like interspecies drift coupled with dissipative phenomena, okay? Now, an equation. Bear with me. What I'm trying to show you here is that all of these instabilities that I've told you about, they all come from the same dispersion relation for magnetized plasmas, okay? All of them. So you have ion dynamics on the left, then you have, and like this is the dispersion relation, what is it? It's like a relation between the frequency of your wave, omega, and the wave number, k, okay? So you have ion dynamics on the left, non-neutral effects is the yellow box there, and then you have electron dynamics on the right. Now the psi term, which is horrible, is horrible, but understand what I'm trying to say here is that if you simplify this psi, it's like in order to consider like an homogeneous plasma without parallel propagation, okay, you're getting the form which is suitable to study ECDI, which is a stream instability, and also it's like an instability that occurs like close to resonances with the electron cyclotron harmonics. Okay, if you don't consider plasma inhomogeneities, but you keep parallel propagation, then you get a dispersion relation which at low frequencies is suitable to study modified to extreme instability, another extreme instability. Then if you don't keep parallel propagation, but you keep plasma inhomogeneities, yellow boxes, okay, you get like an extension to shorter wavelengths, also to shorter wavelengths if you want, but you can also generalize it to longer wavelengths, of the Simon-Hall, what I was saying before, the modified collisionless Simon-Hall, which is a drift gradient instability. And in this formulation, only perpendicular gradients. Okay, so what did we do? Because now the picture seems like quite complete. So is there any space for research? There is, trust me. And also what we did is like starting from a fluid model, and don't trust Alberto, they do work, okay? What we did is like, okay, we obtained from a fluid model, which is like quite limited because you're limited in the long wavelength regime, you know? Quite long wavelength regime. We obtained like a dispersion relation which retain perpendicular inhomogeneities, collisions, which usually in kinetic formulations, you know, are not really present. And then we also kept gyroviscous and inertial effects that give you some final armor radius correction, so allows you to move a little bit further into the semi-short wavelength. And what we added is our novelty is the yellow parameter there, the yellow term there, which takes into account parallel propagation, which was, okay, already modeled in the literature, but also parallel inhomogeneities of our plasma. Is all of this effort worth it? Yes, because look at like this is a very, very beautiful plot from a simulation which is not mine, which is like I without shame stole from Pedro, my colleague Pedro. As you can see, this is like a plot of the electron number density in a magnetic nozzle. As you can see, it is highly two-dimensional, so we do need to account for parallel gradients. Now here, what I'm showing you, very briefly, this is like we applied our model, our dispersion relation, local, linear, fluid, whatever. We applied it to the magnetic nozzle to various points in these 2D plots, and we got some maps for a peak growth rate, okay? And then it's related, you know, real oscillation frequency. So you can see that both the growth rate and the real frequency are both in the like lower hybrid, so lower hybrid drift instability once again, whatever that means. And then also like the k theta for these peak growth rates is quite high in some regions, so this justifies the need to include final armor radius effects. And lastly, we see that like the K parallel is not that important. And this is quite novel because in magnetic nozzles, usually you don't have the conditions for perpendicularly homogeneities driven instabilities. But with parallel gradients, you do have the condition and you don't need to have parallel propagation, which is consistent with some results that we've seen and obtained experimentally also in this university. So all of this, then we applied it to a quasi-linear model, okay, which is like trying to assess nonlinear effects through the results of linear theory. Okay, and we got an expression for the cross-field electron transport. Great. And I'm going to present this at the upcoming IPC, and then we're going to publish a paper on this. Now, the next steps, what are they? Moving to global, because there is nothing left to say about local linear instability. So we're going to move to global with the nonlinear kinetic peak code of Alberto and Enrique. I swear I'm going to do it. Then to compare the results that we're going to obtain with that code with the linear theory that I've shown you up until now. And this is like the last one is like something that I would like to do. Let's see if I can, to extend all of this analytical work to global, to account for, you know, global finite plasma length effects. So, you know, global linear analytical model. And that's everything. If you have questions.